Once again, you are all welcome to this session of vector calculus. And for vector calculus, we are supposed to tackle divergence of vectors and the curl of vectors. But before we do that, we need to go through the principles of differentiation and the integration of functions. So in this section, we're going to look at differentiation, integration of multivariable functions. And then with our earlier knowledge, where we have single variable functions, for example, for single variable functions where y is a function of x. To differentiate this function, we use dy dx, which is equal to f prime of. For example, if you take an example of, let's say, y equal to sine x squared, sine x squared. Find dy dx. In this case, we are going to differentiate, because a single variable function, we differentiate the function y, which is sine x squared dx. And that one will give us, this is a chain rule, there's a chain rule here. So this one is going to give us, if you differentiate sine, you're going to get cos x squared. Then because there's a chain, which is x squared, you multiply it by the differentiation of the chain. That gives us 2x. So that completes differentiation of single variable functions. Today, our main focus is on differentiation of multivariable functions. So in this case, we can have the function, let's say w, which is a function of, let's say, x, y, z. It can be two or more variables, but we are taking three for us to be able to go through. And so, to differentiate multivariable functions, what we do is that we differentiate one with respect, we differentiate the function with respect to each of the variables. In doing so, we keep the other variables as constant. And so to do that, we introduce you to partial differentiation. Partial differentiation. So in partial differentiation, like I said earlier, we differentiate the function with only one of the variables. In doing so, we keep the other two variables as constant, and we treat them as constant. So here, since we have multivariable functions which has three variables, then we can differentiate for each of the variables. So we'll look at the first one. We can differentiate, partial differentiation. The symbol is partial. So we are going to differentiate partial differentiation of w with respect to x. We can differentiate the function w with respect to x. And so the symbol for partial differentiation is what we have written. And so when you see this symbol, it means that the function that has been given is a multivariable function, and we are differentiating with respect to only one variable at a time. We can also differentiate the function, partial differentiation of the function w with respect to y. And then we can also do the partial differentiation of the same function, partial w with respect to z. So in this case, if you differentiate a partial differentiation of w with respect to x, then we keep the variables y and z as constant, and we treat them as natural constants. Let's take, for example, given the function w equal to 4x squared y cubed z minus 3x z squared plus 5x cos y. Find the following. Find 1 partial w partial x, 2 partial w partial y, and then 3 we do partial w partial z. So if you take the very first one, the solution will be like this. We are going to differentiate the function with respect to x, and as we learned earlier, we are going to keep the variables y and z as constant. So let's go ahead. So we have partial w partial x. It means that we're going to differentiate the whole of w with respect to x, and w is given as 4x squared y cubed times z minus 3x z squared plus 5x cos y. Partial x of 4x squared y cubed z, then minus differentiation partial x of 3x z squared plus partial x y. And so at this stage we're going to take them one by one. But let's be careful, we are only differentiating with respect to x. So all the other variables remain constant, and we treat them as any natural constant. So in this term, you can see that 4 is a constant, and we are differentiating with respect to x squared. And so 4 is a constant, y cubed is a constant, and z is a constant. So with constant multiple rule, what we do is that we bring the constants out. So we bring the constants, which is 4y cubed z. What is left is we differentiate x squared with respect to x. Now this one becomes a single variable that we are differentiating. So we can use the partial sign, but it is better to use the ordinary sign. We are differentiating x cubed, x squared with respect to x. And then when we come to this place too, we see that we are differentiating with respect to x. So 3 is a constant, z squared is a constant. So we are left with differentiating x with respect to x. And the last one, we are also differentiating term with respect to x. So we say that 5 is a constant, cos y is a constant, and we are left with differentiating x with respect to x. So now let's do the differentiation. If you differentiate x squared with respect to x, we're going to get 2x. So we get 4y cubed z times 2x minus. Now, if you differentiate the x, it becomes 1. 1 times this term will give us minus 3z squared. Plus, now, if you differentiate the s dx, we are going to get 1. So, plus 5 cos y. So, if you tidy up here, eventually you're going to get 4 times 2, which is 8x y cubed z minus 3z squared plus 5 cos y. So that gives us solution for the first question, that is differentiating the function with respect to x. To recap, what we just did was that we took the functions and then differentiated them term by term with respect to x. And so all terms that were in y and z, we kept them as constant, and we treated them as constants. Now we'll take question 2. Question 2 says that we are differentiating the function with respect to y. That is, we are differentiating respect to y. So we're going to have partial, this is number 2, partial w partial y, which means partial w and partial y. W is this whole term, so we put it there. But like we did in the first one, we have to differentiate them term by term. So we'll have 4x squared y cubed z minus partial y of 3x z squared plus partial y of 5x cos y. And so, as we saw earlier, we are differentiating this, in this case, differentiating with respect to y. So all the terms in x and z becomes constant, just like the 4. So you bring the 4x squared z outside. Then we left with differentiate y cubed respect to y. That is, we are asked to find the differentiation of w respect to y. It means the partial differentiation of w respect to y. So question 2 becomes partial w partial y. And so partial y. And then w is this whole term, which is 4x squared y cubed z minus 3x z squared plus 5x cos y. And so, like we learned earlier on the first example, we need to differentiate them term by term. That's the sum and difference rule. So we separate them. So we're going to have partial y of 4x squared y cubed z minus partial y of 3x z squared plus partial y of 5x cos y. So in this case, we are differentiating w respect to y. So it means that for this question number 2, we have to be careful and take the constant. And the constant in this case will be terms in x and z, and then the natural constant, which is 4. And so 4 is a constant, x squared is a constant, z is a constant. Then what is left is that we are differentiating y cubed with respect to y minus. Now, here is very interesting. We have the term 3x z squared. There's no y term. And so this whole term is a constant. And we learned that if you differentiate a constant, you get 0. So this whole term, if you differentiate respect to y, you get 0. Plus, we are differentiating this last term with respect to y. So 5x becomes constant. You bring the constant out, then we are going to differentiate respect to y cos y. So let's do the differentiation. So we have, in this instance, we have 4x squared z. If you differentiate y cubed with respect to y, you're going to get 3y squared, right? Plus, now, if you differentiate cos y, what do you get? We're going to get minus sin y. Minus times positive becomes minus. So we have minus 5x sin y. And so we need to tidy up. By tidying up, we have partial differentiation of y respect of w respect to y becomes 4 times 3, 12. 12x squared y squared and z minus 5x sin y. So that is how we do the partial differentiation of w respect to y. Like we said earlier, all other terms, all other variables become this constant. We treat them as constant, which is x and z. So we'll move to the last one, where the last one we are asked to differentiate w respect to z. Find the partial differentiation of w with respect to z. So this one can go off. We take this one off, and then we do the last one. The question 3. 3 means partial w, partial z. And so z, partial w is this whole term, which is 4. And as we did earlier on, we can do it term by term. So 4x squared y cubed times z minus partial z of 3x z squared plus partial z of 5x plus y. So in this case, let's also be careful because we are differentiating w with respect to z. So wherever we see a natural constant or variables x and y, we treat them as constant. So we can bring them out. 4 is a constant, x squared is a constant, y cubed is a constant. Relative. Differentiate the z with respect to z, right? Differentiate z with respect to z. And then here, minus 3x is a constant. So we are going to differentiate with respect to z of z squared, right? And the last one is, you see that we are differentiating with respect to z. And if you look at this term, there's no z in it. So this whole term, 5x cos y, is a constant. And you treat it as a natural constant. And so if you differentiate a constant, you get 0. So you get 0. Now let's tidy up. So we have 4x squared y cubed. And then if you differentiate z with respect to z, you get 1 minus 3x. If you differentiate z squared with respect to z, you get 2z. So finally, if you differentiate w with respect to z, you are going to get 4x squared y cubed minus 3 times 2, which is 6xz. And so that is how we do the partial differentiation. And so I hope we've learned something from here. It means that let's be careful that differentiating with respect to z, then all variables in x and y, you keep them as constant. So that is how we do partial differentiation. To end this lecture, we are going to do partial, we're going to take integration of multivariable functions. And the principle too is the same. We always integrate with respect to one variable, and whilst we keep the other variables as constant. So quickly, we're going to do integration of multiple variables. We just saw how to differentiate multivariable functions by using partial differentiation. This section, we are also going to look at integration of multivariable functions. And the principle also remains the same. We can integrate with respect to only one variable at a time. So if, for example, we have the multivariable function w, which is a function of x, y, z, it can be 2 or more variables. But we are taking 3 variables. And so we can integrate w with respect to x. We can also integrate w with respect to y. We can integrate w with respect to z. You can also put a partial differentiation sign to show that it's a multivariable function, but you can also keep it like this. So if you take, for example, given w to be equal to 5x squared y cubed z squared plus 4x cubed z are 4, then minus 3 3x exponential y. 3x exponential y. So if you are asked to integrate with respect to x, y, and z. This is how we do it. We take the first one, we integrate w with respect to x. And so that will be integrate w is giving us 5x squared, x squared, y cubed, z squared, plus 4x cubed, z squared, z4 minus 3x exponential y. We integrate it with respect to x. I put this partial sign to show that we are integrating with respect to x. So we keep the other variables as constant. So let's do it term by term. So we integrate 5x squared y cubed z squared with respect to x plus integrate 4x cubed z4 with respect to x minus integrate 3x exponential y with respect to x. And so this is how we do it. You see that in this case we are integrating with respect to x. So 5y cubed z squared remains constant. So we can bring them out. So we're going to have 5x squared z squared integral of x squared dx plus we are integrating with respect to x. So 4 is a constant, z4 is a constant. Then integrate x cubed with respect to x. Then the last one is that we are integrating with respect to x. So 3 is a constant, exponential, and y is a constant, it comes out. So we are left with integral x dx. And so let's tidy up. We're going to have 5, this is 5y cubed, sorry, this is 5y cubed z squared. And so to integrate this one, we're going to have 5y cubed z squared, which are the constant. If you integrate x squared dx, you get x cubed all divided by 3, right? And then plus 4z raised to the power 4. After integration, every integration comes with integration. After integration, we have a constant of integration. But in this particular case, we kept two variables as constant, which are the y and z. And so our constant of integration will be a certain function, let's say h in y and z. That is how we do the integration. So this is what we get if you integrate w with respect to x. That is keeping y and z components as constant. And then after integration, the constant of integration becomes function in both y and z, because we kept y and z as constant. And so we can take the second example, that is integrate w with respect to y. Let's quickly do that and then we make progress. So if you take the second one, where we have going to integrate the second one, integrate w with respect to y. We're going to have integrate 5x squared y cubed dz z squared with respect to y plus integrate 4x cubed z4 with respect to y minus integral 3x exponential y with respect to y. And so like we did previously, we see that 5x squared, z squared are constant. And so we need to integrate y cubed respect to y. So we're going to have 5x squared, z squared, which are constant. And integrate y cubed respect to y gives us y raised to the power 4 over 4. Plus, now if you integrate 4x cubed z for respect to y, there's no y component here. So this one is treated as a constant. And we treat it, if you integrate a constant with respect to a variable, the answer you get is a variable, is a constant times a variable. So this one becomes 4x cubed z4 times y, times y, times y, right? Minus this one, we are integrating with respect to y. 3x is constant, so 3x comes out. Integrate exponential y dy, you're going to get the same thing, y. And so now, class, we can guess what will be the constant of integration. In this case, we integrated with respect to y. So it means that variables in x and z becomes their constant of integration. So we'll add the function x and z. This is the constant of integration. That is. And the last one, before we draw the curtain, we will look at integration of w with respect to z or z. And so that also follows the same trend, dz. And so that will give us integral of 5x squared y cubed z squared with respect to z plus integral 4x z minus integral 3x exponential y respect to z. So in this case also, like we learned earlier previously, realize that we are integrating respect to z. So any variable you see in x and y become our constant. So in this case, our constant becomes 5x squared y cubed. We'll be left with integration of z squared with respect to z, and that will give us z cubed all divided by 3. Plus, now here we are also integrating with respect to z, meaning 4x cubed is a constant. Bring the constant at 4x cubed constant, and you integrate z raised to the power 4 with respect to z, and that will give us z raised to the power 5 over 5. And the last one, we are integrating 3x exponential y with respect to z. From this term, we can see that there's no z term. So this whole term, 3x exponential y, is a constant. And so we learned that if you integrate a constant, you get the same constant times the variable. So in this case, we get 3x exponential y times z. And as usual, we shouldn't forget about the constant of integration. In this case, we integrated with respect to z. And so it means that all variables in x and y become our constant of integration. So we can have a function g of what, x and y. And so that gives us the integration using multiple variable functions. So on this note, I hope you've gotten how to integrate these functions. And I thank you once more for your attention. See you in the next section. Bye.